All right, so let's now get into example 2 along our topic on continuity of a function at a specific point. So this problem in example 2 that I'm about to introduce here is quite popular among many textbooks out there, and especially among those commercial web programs that offer online homework. For example, WebAssign, MathML, or especially for students who are in the state of Washington. Then about 7 to 8 years ago, instructors in the state of Washington started using a lot of a web program that's called ymap.org. And so my bottom line here is that the problem came out from example 2 right here are quite common and especially popular among all the WebAssign or MathML or even YMAP right here. So now since these problems are in the electronic version, so allow me to bring up my computer screen and we will be having a direct look at them. All right, so here's my computer screen right here. So go ahead and observe the wording here of the problem. But in the wording of the problem, the graph below is the function f of x. So here we have a graph. And now the particular web problem that I'm bringing up here is specifically from ymap.org here. But like I'm saying, you can surely find a very similar problem right from WebAssign or sandgauge.com or MathML whatsoever. But this particular program I'm using that with YMAP has a feature that I can zoom in the graph right here. So this is the graph for f of x. So have a good clear picture of that, and you can even pause the video to take notes of the picture of the graph. But now, once everybody have a good clear note of the graph, the question is asking us, determine which of the following rules for continuity. So remember, earlier in this lecture, I talked about being able to say that a function is continuous at a point. Then we need to satisfy, the function needs to satisfy 3 rules. However, recall for yourself that when I was writing down those 3 specific requirements or rules for continuity at a point, then there was a certain order of how those rules are being carried out. But here, the good thing and the part that I really like about this kind of problem, and I would like to bring it out as an example in class, is that the author of the problem purposely shuffle the order of all these rules. So all you see here is simply just rules, rule, and rule. It is your responsibility to know which rules comes first, which rule comes next, and which rule is the last out of all the 3 rules right here. But the way how it's written or the way how these rules are written are quite standard. And so simply just look at these rules and compare that with your notes that you've taken earlier. But now back to the main goal of the problem. We want to determine the graph given here, which one of the rules for continuity being listed here is being violated. So violated means it's not true. So is this rule not true, or is this rule not true, or is this rule not true for this function at the particular point x equals -1. So have a moment to clearly understand the goal, the purpose of this problem, and we are going to proceed. All right, so let's now proceed. And like I said, so maybe right now all these 3 rules are being written quite like the way how I was writing it down on my lecture earlier, but in other problem that I'm later on going to bring up, then these rules might be shuffled in a different order. So now all we have to do in our responsibility in order to find the correct rule that violates here, then first of all, at x equals -1. Now allow me to bring part of my other board up here. All right, so for the graph of f of x, let me find a way to bring up the graph here. All right, so for the graph of f of x, then the way how it looks, then the way how it looks there, then f of -1 has a value. And you can see that back on your point right here, this solid dots on the piece of graph, even though the graph itself is a piecewise function, but when x equals -1, we do have a solid point. So that means f of -1 is defined. I don't even need to worry about what the output value is, but now I can guarantee that f of -1 is defined. So that means back in our understanding, let me put the graphs away, then the rule here, the first rule here, it looks like among the list here, f of a is defined, is not violated. So we don't want to choose that. Remember, what we're looking for is which rule for continuity is violated. Which rule is violated at x equals -1. And so for now, among the 3 rules being indicated here, first rule is not indicated, so I am not going to choose that one as a multiple choice. And this problem in particular on its own is designed as a multiple choice. And so let's look at the next rule over here. And allow me again to bring up the 2 boards so that I can work out the solution a little bit. But now if we're looking at the graph again, now if we're approaching this function, if we're attempting to take limits of this function as x getting close to the limit point -1 from the left hand side, then with your experience with limits at this point right here, anyone reading the graph should be able to estimate that this limits from the left hand side of -1 is going to give limit -2. And same function, but now if we're finding the limit of the same function as by letting x coming close to -1, our limit points, but from the right hand side, then this function comes to limits equals -3. And so that means generally speaking, from 2 sides, then this function has the limit of this function f of x for x coming close to -1 generally from both sides is a non-existing limit, or our popular kind of answer, popular kind of expression here is DNE. Sorry about the interference, but and so in that way, now that tells us that back in our, and let me put the map away, let me put the graph away, and completely stay on the graph right here. Then this requirement here fails. Limit of the function here when x comes to a for this particular problem, for this particular graph right here, the limits here, the limit f of x exists, but this is a violation because it did not exist. We have proven earlier that it's not a non-existent limit. But now before I make my answer choice, think about it. The consequence of having this is that if we fail having a limit, then of course this requirements that back in my definition of continuity, I call this is rule number 3 right here for continuity. This rule number 3 for continuity also fails. So meaning for this kind of graph right here, for this kind of graph, then we have rules 2 and rules number 2 and rule number 3 are both failing. But now since the problem itself, the problem is programmed. Here's the good thing about the problem. This problem here with Y-map that I'm using is smart enough to tell between these 2 rules which one is the higher is at the higher priority. Meaning, of course, if either one remind yourself what I said earlier about, if either one of the first 2 rules, rule 1 and rule number 2, fails, then automatically we will have rule number 3 being will fail as well. And so here in this particular problem, what I'm trying to say now is that even though we have both of these rules are failing, but we need to pick the one that has higher priority. And higher priority means it's the first reasoning that leads to failing a continuity. And so that means among these two, that choice in the middle, the limit doesn't exist, is higher priority compared to this, because this bottom one right here is simply a consequence. This bottom rule fails simply as a consequence of this middle rule fails right here. And so in that way, that's how we can tell the correct answer. And so allow me to bring up the actual answer for that. And yes, the rule that's being violated here, limits exist, but it does not, as I proved earlier. And so let's bring ourselves into another one. And let's bring ourselves into a different graph right here. All right, so in a graph like this, and in the same example, we still stay in the same example, example 2, then let's call that for your own. If anyone taking notes, you can go ahead and call this problem example 2, but part B. So pretty much the same problem, except for we switch to a different function f of x. And it has a completely different graph. So it's a different function. And so if you look at the list of the rules for continuity, this time it's really emphasized what I said earlier about the usefulness thing about this. The problem is that it purposely wants you to be able to find among all these three rules which one has higher priority and which one is the last one in terms of priority. And so same goal of the problem. We want to determine which one of the following rules for continuity is violated at x equals 2. Okay, so the point that we want to consider here is x equals 2. So now f is being defined, or the function exists, I mean the limit of the function exists, or the limit equals to the function value at the point. Which one of these is being violated? And so now let's bring up the graph a little closer. And I am going to bring up that all right. So for example 2 part B here, once again, we want to find out, can we substitute x equals 2 into the function? And so x is, if you're looking now at the graph right here, at x equals 2 on the graph, we have an empty hole right here. Okay, and there's no, right on that vertical line, there's no special other points being placed somewhere, and that means this function value is undefined. So that function value is undefined. And so having that function value being undefined, now let's look back at the entire graph here in general. Right. So having this statement here, this rule being violated, because the rule itself is we need f of a's to be defined, but now what the violation here is that it's undefined, as we just found out. So being undefined here also leads to the function limits won't be equals to the function value at f of a, because we won't even have a value here, even if we can find some limits. And so in that way, between these two, so once again we run into two different reasons that our function fails to be continuous. But among the two reasons here, the bottom reason and this reason on the top of our list here, this bottom reasoning is the one that's at higher priority, meaning because we have this rule for continuity fails, that will automatically lead to the other rule being failed. And so that's why this one I chose here as my choice is the one at higher priority. And once again, this is how Y map is going to agree with that. And also I'm sure that if you run into the same problem, the similar problem with WebAssign or the MathML or any other commercial online web assignments right there, then it should be behaving the same way of how the problem is giving you the correct answer. All right, so that's how we're done with example 2, part B. Let me bring everybody into another problem in the same example 2 right here. So let's look at a different graph. So the graph we have this time. All right. So here we have a graph. And now I'm once again going to bring up the two boards together, my other board. All right, so the way how my graph looks, then you can see that when x, and we can call this part C of our example right here, but the function value at 2. Observing the graph, you can see that we do have a solid point when x equals 2, and that solid point is at the height 2 as well. So here we do have, this is our input, and we have a successful defined output. So that means our function is defined at x equals 2. And so the rule about f of a is defined, this rule is not violated. So we, among our list of which rule being violated, don't choose this one. This is not the correct choice, you can see. So now, then, if first rule already passed, we have to move on to the next rule. Then let's observe the graph again. So with this graph right here, this time let's take a look at the limits. And with your experience doing limits by observing graph at this point, when we're approaching 2 from the left-hand side, this graph comes down to a vertical height being 1, and from the right-hand side, meaning taking limits of the same function, letting x coming close to 2, but from the right-hand side, that also comes down to 1. So limit from the left-hand side and limit from the right-hand side, they both agree to an overall limit being 1. And so that means our function here in particular has an existing limit. The limits for x getting close to this limit point 2. From both sides, this is an existing limit being 1. So I have to make a note here as an existing finite limit. So in that way, rule number 2 is also satisfied, meaning no violation for rule number 2. No violation for rule number 2. I have to make it clear in that. Okay. So no violation for rule number 2. And so in that way, so this rule is not our choice. No violation here, so that rule is not our choice. Let's look at the third rule. So on Y map, the third rule is indeed being shuffled and being placed in the middle of the list. But that's okay. It is at this point our responsibility to be able to find out, among all these 3 rules, which one has the higher priority. And so now the 2 higher priority rules have all been satisfied. So let's look at the last rule right here. So allow me to erase the board here. So after looking at requirement number 1, function output equals 2. But the limit of the function when x was coming close to 2, generally from both sides, that was at limit 1 right here. And so in this case, we can see that limits for our function when x comes to, and I should have, when x comes to 2 equals, actually is not equal to the function output's value at 2. This is one thing that is so clear, nobody can argue about that. And so now let me get back completely on the computer screen here. All right, then with our computer screen here, then the correct answer choice at this time is going to be this last one, this middle one, this one in the middle. See, the statement says the rule says we need the function limits of the function as x comes to that limit point equals to the function output value at a. But it was a violation in our case here, and this is the only violation for among all the three rules right there. And so that's how we made our choice for that, and that's the correct answer. And so now at this point, you have had most of your understanding regarding continuity at a point for any function. And so now another terminology need to come ahead for here. I need to introduce another terminology, or basically, or actually as another definition. So let's have our next definition, because continuity we have learned so far is only continuity at one single point. But a lot of time we generally talk about a function being a continuous function, but did not specify at which point that is throughout its own domain. And so now let's come up with a definition for what it means by being a continuous function, simply a generally a continuous function anywhere on its domain. And so a function f of x is said to be, and in my red ink, said to be continuous. And of course, when we're saying continuous, we're looking at in its domain, any function, and at this point in your learning, you must know what the domain of a function is. And so a function f of x is said to be continuous, of course, in its domain, if f of x is continuous at every x value in the domain of f of x. All right, and so that's simply what it means by having a function generally be continuous. And so now I'm gonna, after looking at this definition, allow me to introduce, allow me to bring this concept of being a generally continuous function, and let's find out among all functions we have learned up to this point of your learning in math here, then which function is regarded as a continuous function and which function is not. So at this point in your learning in mathematics, you have seen polynomials. All right, and so polynomials, and then you have seen rational function, or for short, I call them the rationals. Let me readjust my writing here. Polynomials, rationals. You have seen functions that involve roots. For example, square root, cube root functions. So roots. You have seen trig function. Okay. And trig functions allow me to make a brief reminder in some of our earlier discussion right here, but in some of my, I do believe in some of my earlier lecture, I mentioned that for example, sine of x, if we're taking limits as x coming to any limit point a, then we have the the output, we have the limits coming out to be happen to equal to the function output at A. And so now if we're looking at that a little closer and blend it together with our understanding in terms of continuity, then that was a way to guarantee for us from the earlier point that wasn't. So from what we understood earlier, then this is now an explanation for why our trig functions are continuous in their domain here. So the same with cosine function. So cosine of x, and we had some brief investigation earlier, and we came to a conclusion that for cosine of x, that you're letting x coming close to any limit point A on the x-axis, then the limit coming out happens to be exactly equals to the function output value at x equals A. And so that also can be used as a brief explanation for why our cosine function right here is being a continuous function. And so generally now we can extend that concept and have a broader understanding that trig functions are in general continuous as well. But now here I'm on my way to remind everyone about the kinds of functions we've been familiar with so far. So there are trig functions. There are, and how about inverse trig along the way? Inverse trig functions. Okay. They are exponential functions. And they are logarithms function. So this is a reminder of the kind of function we have experienced with throughout ever since your beginning day of learning math up until this point when you are now in calculus. So after we've learned about continuity, then there's a theorem that says, this is now a theorem. It's a truth being guaranteed. A theorem is something that guarantees a truth and being proven. We don't need to see the proof here along any of these lectures, but in some other supplementary videos, then I'm going to have proof for these. But in this theorem, I'm going to start out by saying any one of these, right? Any one of these functions. So those are the polynomials, the rationals, the roots function, the trig function, and including the inverse trigs, the exponential functions, and the logarithms right here. All of those functions, families of functions, are, so this is one statement right here, all of these functions, or any one of those functions, are continuous function on its domain. I should have said this is continuous on its domain. And that is our definition. I mean, it's a theorem that can guarantee the truth. So now, once we have this theorem and looking at it, what is useful about this theorem? So now let's find out what's useful about the theorem I just now introduced. Let me now bring everybody into example 3 right here. And here's another example where we're going to be back to just simply the marker and the board here. But knowing the theorem just now allows us to even evaluate limits for other kinds of functions. It sort of allows us to be able to do more limits problem right here. So let's evaluate the limits of how about sine of x over 2 plus cosine of x. And let's say we want to get x getting close to pi. So now back to what I said earlier. Before learning about this theorem, before knowing about this theorem, so this theorem is sort of like a way to guarantee that anytime we are working with any of these functions, then they are guaranteed for sure to be continuous functions on their own domain. And so how is this theorem useful in our particular example here? Because if we're having, and of course this kind of limits problem was never brought up in any of the earlier lecture before this point, prior to this point. But now, if we're having a closer look into the actual function on its own right here, this function has a quotient where limit law has a rule that we can handle a quotient. And then if we go further into, applying the further limit laws, eventually we're gonna run into handling limits on trig function. And now, once again, back to the theorem itself, that we know that trig functions are being classified among those that are being continuous in their domain right here. And so now, let's really get into it. So limit laws allow me to separate this into two separate limits problem. So we want to find limit as x getting close to pi for the function sine of x in the numerator. Okay. And divide that by the limit of this function in the denominator, 2 plus cosine of x, as x is getting close to pi here. Okay? And so the next step, we are ready for tackling down the limits for this particular function. Now, first of all, if we apply our understanding previously to the theorem, we apply that theorem we just now learned here into our problem, then this value pi is in the domain of this function sine of x. And so therefore, this limit now can easily be found. And of course, we also learned how to find the limit for something like this in earlier lecture as some of the other limits right there outside of the polynomial. Then this is simply just sine of pi, and we know that. Okay. Limit laws in the denominator can now guarantee for us that we can break that into limit of the constant function, letting x get close to pi, plus a separate limit for the cosine of x function. It never hurts to break things into small steps like that. And so you have seen limit laws that can quickly find you an answer for this. And this will work similar to how we've found that answer in the numerator. And so now in my next step, I am going to end up with this is sine of pi. I hold on to the actual evaluation step until all the way at the end. But in the denominator now we having 2 plus and cosine of pi. It's all due to the fact now we know that cosine is a continuous function, a function that's continuous everywhere in its domain. Plus, we already knew from earlier lecture that cosine is a simple function that we can just simply plug the limits point into the function value as a function value. And so now sine of pi is 0. In the denominator, we're looking at 2 plus cosine of pi is 1. I mean negative 1. Right? And that now is all, break it down to 0. Okay, and so prior to learning about continuity or what it means by being a continuous function in its domain, then we were never able to handle a limits problem like this. But now after we've learned carefully the concept of being a continuous function, then here we are able to find the limits on this problem. It sort of extends our own understanding. And I remember when we begin our lecture about continuity, I said that we apply our limit understanding on top of this old concept. But now think about once we've done with that, applying our limit understanding on top of the old concept, then that even extends for us into, give us more flexibility in terms of finding more limit problem, being able to evaluate more limit problems.